go. Are we recording? Oh, for a minute I thought we weren't. Okay. So, once again, welcome to another fun adventure with data mining. So I've got some data here that I borrowed from a archaeological dig that had recorded some data on different sites that they were digging at and where they found stuff at. So this is the depth they found items at. Clearly this is not in feet because they're not going to dig down 120 feet. I believe it was in centimeters, to be honest. Or maybe it was in inches. No, it was in inches. Sorry. I should have labeled my units better. Anyway, and so they have a couple different sites they're looking at, and so you might want to ask yourself is, hey, are all of my sites the same, or is one of them significantly different from the other? A great way to test something like this or would be to use an ANOVA. So remember with an ANOVA, our assumption or our assumptions we should probably check, but I'm not going to bother them with them. I'm going to assume that my sites and my discovery of items are independent since they seem to all look different. And that they're random sampling since you can't really predict where you're going to dig something up in the ground, which is kind of funny. And I'm going to assume that I have normal residuals and that their variance is about different. Actually, I should probably check that one because that's a good one to check. So let's go up to stat and go into basic statistics and display descriptive statistics. And I'm going to look at depth sorted by site. And then the statistics I want is, I'm going to look at the mean. I don't really want to see the sum of squares, the min, or anything like this. I just want to see my standard deviations and my variance to see if those are different amongst all my sites, because if they are, then this might not be an appropriate test to use. So we're going to go ahead and hit OK, and hit OK a second time. Oh, my standard deviations are pretty close. My variances, there's one that's a little off from the rest of them. These two are both pretty close, and these two are both pretty close. It's probably okay. If this were something more serious, I might be a little more concerned since, these two seem to be a little bit different from the other one. But that might be detected by my ANOVA as well. So, this is just to gain some insight as to whether or not the ANOVA is going to come up with anything for us. So remember, the ANOVA always starts with the hypothesis that all of my means for all of my sites are the same. So I'm going to see if at least one of them, as my alternative, is going to be a different depth on average. Let's take a look at this. So I'm going to hit stat and notice ANOVA gets its whole little thing because there are lots of different ANOVAs. There's nested, there's general, there's all kinds of these. I am going to just start with the basic one-way ANOVA. And so since all of my data are in one column and all my factor levels, or what all of my different groupings are going to be, are in another column, I'm going to be choosing this option. For my second example, I will be doing one where the response data is actually in separate columns. So this is the one column. My response is depth, and then my groupings or factors are set by site. Now, as you look at this, you might be like, ooh, well, there's lots of buttons to push here. Let's see which ones I want. I'm going to go into options. I'm going to leave this at a 95% level of confidence. You can change this if you want to do a different significance level, like a 99% or a 98% or a 90%. 95 is pretty standard. The reason I'm going to do that is I'm going to also produce some graphs that use a confidence interval for each of these. So I have checked interval plot because I like to look at the interval plot when I compare my different levels or factors or groupings to see if it appears like maybe one of them is different from the other, to kind of judge my hypothesis, simply because your hypothesis is, are they different? Well, assuming they are different, and then your alternative is that one of them must be, and it's very difficult to detect which one will be. And then notice there's these options for all these residual plots. Remember, in order to come up with a correct ANOVA or ANOVA that's appropriate for your data, you have to make sure that your residuals look normal. And I like to use the normal probability plot for that, but I'm going to select them all just because, you might want to look at them all. One of these is probably going to be your favorite. They all represent fairly well what you want. And if you're worried about which one you should be looking at, I did give a description of each of those in the ANOVA document along with data for this week. So that's fun. And now I'm going to go ahead and hit OK because those are the only options I really care about right now. For graphs, I'm not going to do any comparison or results or sort or anything else. I'm just going to go ahead and go with what it is, and I'm going to show you a comparison test in a little bit. So let's hit OK and see what we get. Ooh, we got lots of plots to look at here. Uh-oh. So, as you're looking at this, you might notice for your confidence intervals, excuse me, Two of them are much higher up than the other. So as I'm looking at this, these two look very close. And these two are fairly close, but this one is much higher up compared to the other three. So I'm suspecting that probably number one's going to cause some issues, if anything. But it might be that there's enough variation amongst all of them that it doesn't matter. So there we go. The next thing you got to ask yourself is, did my residuals look normal? Otherwise, I am not using an appropriate test. So I usually check the normal probability plot, which just compares your residuals against what a normal distribution would look like with percentages. And if you get something that looks vaguely like a straight line, that means you've done a good job. And then there's a dot there. I usually don't use the versus fits, but what you want to see is that there's no pattern in the variation here. This looks fairly random, so that's good. And this looks all over the place, and so do these two, so that's probably okay. Or you can look at the histogram of the residuals and ask yourself, does it look like a normal curve? And this very clearly looks like it's a lovely bell, so we're probably okay with using an ANOVA for this data. Alrighty, now let's look at the actual ANOVA results. So if we go up here, it's calculated a lot of things for us. There's my F value for my two different degrees of freedom, my 3 and my 4. And my p-value is so small that it didn't actually show up. Oh no. And since I did that confidence interval plot, it also gave me all of my confidence intervals by site. So that's kind of nice. Now, if this is too small for you, you can go up to graph and then probability distribution and calculate the probability for the F distribution. Where is it? Oh, I chose the wrong one. Sorry about that. The F distribution. And then you have to be careful and remember who's in the numerator and who's in the denominator when it comes to doing your degrees of freedom. Remember, your groupings are your by groups and between groups, and make your numerator and denominator. And if you do this backwards, it'll become very clear because your F value won't show up correctly. It's pretty easy to see. Anyway, so my numerator in this case is the 42. And my denominator is a 3. Oh, another quick way you can tell that is, remember, the F value is just the MS's divided by each other. So notice that this is much smaller. The error source is much smaller than the site source. So clearly this is the one I'm dividing by, right? You know. Anyway. So as you look at this, I'm going to check shaded area, and I want to do X value. And remember, the ANOVA is always a right tail. And my value is 15.14. Minitab does round F values to 2 decimal places. If you want a more detailed one, there are other ways to do that, but I'm not going to bother. It rounds like the devil. We hit OK, and there you can actually see your tiny, tiny probability. It's kind of fun. It's interesting that it told me that was 0. I wonder why, because that picture doesn't look very 0. Oh no, and I lost it. Oh, that's great. Well, there's my graph. Haha, I found it again. Anyway, no. Either way, your p-value, quite small, so we would reject the null hypothesis. So it would appear that there is evidence that my sites, on average, do not have the same depth of where you would find excavated items. So one of them is not like the other. So you might ask yourself, how can I tell who's different? So we've got some inkling to that by looking at our confidence intervals. It appears that this one and this one look different, but this one, it's questionable, right? It's kind of close to 2 and 3. So 4 might not actually be a problem. 1, I suspect, is highly likely to be a problem. So the easiest way, I think, to check this is to actually do what's called a Tukey test. So we're going to go back to Stat, ANOVA, and go to One-Way ANOVA, and we're going to use my favorite comparison test. There are lots of these. You might, in your future, probably try some of the other ones, but my favorite is the Tukey because it is incredibly easy to read. And you can make him do some different options, like actually show you the test results, or, you know, interval plotting to give you the differences of the means. I like to use the grouping information because it is quick and easy and a dirty way to get this done, to tell who's the difference or the odd man out of the different comparison levels to determine, which site is going to be the one that goes as a problem. So we're going to hit OK, and we'll hit OK again, and up pops a bunch of stuff because I forgot to uncheck those graphs. Darn it! Oh well, so I did it again. Either way. All right, now, pairwise Tukey comparison. This is interesting, very interesting. So just like I suspected from looking at the variance and looking at the other values, Tukey warns you exactly how to read it at the bottom. Means that do not share letters are significantly different. Aha! So as you look at this, 2 and 3 are similar because they share letters, And 1 and 4 are similar because they share layers. That was what this is really telling you is actually more information than before you might have suspected of having here, is that actually sites 1 and 4 are similar in nature, and sites 1 and 3, or sorry, 2 and 3 are similar in nature, but they are significantly different from each other. So your groupings of sites are number 1 and number 4, number 2 and number 3, and 1 and 4 and 2 and 3 are different from each other. So that's how you would do an ANOVA on this type of data where it's given to you in a big list. I'm going to open a second worksheet of some different data. I left this one just on my desktop so it would be easy to find, and it is an Excel file, and it is the business startup costs. Open. I hope this one opens nice. Oh, it didn't open with my variables nice. Anyway, so these are the startup costs in thousands for some different businesses. I do not remember what each of these stand for. I am going to pause this video. I don't know where the button went to pause. Hold on. I gotta go down and grab it. Pause. Because I'm gonna have to go look up what these are. Okay. Back to recording. Sorry about that jump. So I looked this up and this is what they actually stand for. Sorry about that. I should have had that in there ahead of time. This is startup cost for some pizza, and this is a bakery, and clearly these are made up shoe stores, gift shops, and pet stores, so that's kind of fun. It's interesting that we've got some different data in here. So what you want to ask yourself is, hey, is the average startup cost different for these groups? You know, or do they all have the same average startup cost? In which case, hey, it doesn't matter if you sell donuts or if you sell poodles. It's gonna all come out the same. I really shouldn't laugh at my own jokes. That's sort of lame. Anyway, but notice that you don't have your group by or your factor columns or a factor column. You actually have the data already separated. So you're going to have to choose some slightly different things. So I'm going to go up to Stat, go to ANOVA, doing my one-way ANOVA, and here, since I don't have a factor and response variable, instead I'm choosing, hey, my data is already separated in columns for each factor level. How convenient. So my responses are recorded in all of these columns. I double click to do this. Some of you hit select. That's fun. And this should already be set up for all of my options here. So I should already have at 95% two-way, my two-key comparison prepped and ready to go. And then for graphs, I'm going to produce some intervals and my residuals. I actually think I'm going to change my residuals so I just get the one I like and the histogram because that one's pretty easy to read. And other than that, I'm good to go. We're going to go ahead and hit OK, and that should give us everything we need to decide whether or not the startup costs for these businesses differs on average. Don't forget the average part. Another way you could say that is the average startup cost for these businesses is the same, would be your null hypothesis. Your alternative is at least one of them is different. Ready? Let's do this. All right, so I've got a bunch of plots I made. These first two are my residuals. Ooh, that doesn't look very normal. It's kind of all over the place. I'm a little scared because this tail sort of comes off. That means that this is probably not an appropriate test for this data. That makes me kind of sad. So I probably should be choosing a different test to decide what's going on with these two. Oh well. And this doesn't look very normal either. It looks almost like it has a right tail. Oh, and it's a little heavy-ended in the middle. It looks almost bimodal. I'm not happy about that. Okay. And if we look at our confidence intervals, can we detect anybody who might be different? Oh, it looks like, you know, this type of store. What was X5? Oh, pet stores. Pet stores seem to look a little different from the other places. These places all sell like food and this sells something alive, so maybe that's why. Yay! So again, significance level alpha 5%. That's coming from that confidence interval I started with. All means are equal. At least one mean is different. So you can totally steal this off here, but I've been making you write your null and alternatives in detail so that they make sense and they aren't just like a robot produce them. So please write better ones than that. And we're going to look at our F value. Notice it's pretty small, and therefore our P value is also pretty big compared to the B value we saw before. So, but you can compare your alpha and your P value, and you would still be selecting reject since our P value is smaller. So we would reject null, and then we would say it appears at least one mean is different. Let's see what we got here for our confidence intervals. Those are different and pooled. His standard deviation looks pretty nice. Their standard deviations are all pretty close except for X5. That's the one that's got more variation than the other. Or standard deviation. Well, standard deviation is a measure of variation in spread, so that makes sense. Let's scrolly down here to see if anybody turned out. Oh no! Is anybody different? Oh, means that do not share a letter are significantly different. Oh, it not only was 5 different, but 2 was different. Where's 2? I wouldn't have predicted that by looking at this. Huh. Fun times in Math Magic Land. It would appear that I didn't observe something well. See, an X4 almost looks identical to X2. Huh. I am surprised by these results. It might have something to do with its... Let's see, look at it. Let's look at X2's data. Well, he does have a greater variation amongst him. He has standard deviation. He's spread out more. That might be part of the problem. And his confidence interval is a little large compared to everybody else. So that probably has something to do with it. Even the other large one, 4, is much smaller. Well, much, again, that depends on, is it a significance difference? And evidently it is. So it would appear that 2 and 4 are different, or sorry, 2 and 5. So I would say that the startup costs for a pet store and or a bakery appear to be different than these other startup businesses. So there we go. There's how you do the analysis of variance test, also known as the ANOVA. Best name for something ever. I hope you enjoyed this video. See you next time.